Hello students, and welcome to section 10-2 continued. We have discussed the quotient property of square roots, but today we're going to dig in a little bit more. Just to reiterate, a fraction containing radicals is in simplest form if no radicals are left in the denominator. The quotient property of square roots and rationalizing the denominator can be used to simplify radical expressions that involve division. When you rationalize the denominator, you multiply the numerator and denominator by a radical expression. That gives a rational number in the denominator. Okay, so again, we've already discussed that the square root of a over b can be rewritten as the square root of a over the square root of b. And we've also discussed how you can rewrite in this first example the square root of 56/45, again denoting the property from up above, as the square root of 4 times 14, or if you prefer starting with root 56 on its own and then breaking it up as such, but also root 45 broken up as, well, root 9 times 5. As it turns out, as you recall hopefully, the square root of 4, because that's a perfect square, yielding 2, and the same thing with 9, but of course the square root of which giving you 3. We end up then with the following: 2 root 14 over 3 times root 5. That correction, of course, had to be made apparently. So that we're left with this particular fraction. Now, it does work out where you cannot leave a square root in the denominator of a fraction. So what we do is something called rationalizing the denominator. Again, we've discussed this, but multiplying both numerator and denominator by root 5, as you see here, what you'll get particularly in the denominator is root 5 times itself, which is just simply root 25 or 5. You already see that 3, so 3 times 5 then gives you in the denominator 15. The numerator is simply 2. 14 times 5 under the root is simply 70. So final answer, 2 root 70 all over 15. So let's simplify. Now there are a lot of problems here for us to dig into. I wanted to start with something nice and simple. Number 1, for example. We're going to be simplifying. So the square root of 9 over the square root of 18. Now, according to the quotient property, if we start with something under one root, we can split it up into two separate. However, in this particular case, you might want to actually write it in the other direction so that 2 radicals are written as 1. And you can do this. You can go back and forth. So the square root of 9/18 is nice because 9/18 is a reducible fraction, of course, 1/2. Then you can go back, splitting each part of that initial root, or I guess simplified root, as follows: the square root of 1 over the square root of 2. Yet again, as we denoted in the example up above, because you have a root in the denominator and that is not acceptable, if you multiply both numerator and denominator by the square root of 2, again this is called rationalizing, the denominator will end up being the square root of 2 times the square root of 2, or square root of 4, which is 2. The numerator, on the other hand, you just multiply, and in fact you just see there as the final answer root 2 in the numerator, and of course then still 2 in the denominator. So let's continue. Number 2, the square root of 8 over the square root of 24. So again, if we rewrite this as one singular fraction under one root, again the quotient property allows for this, we can see here that 8/24 is reducible. As you see, 1/3. Similar to problem number 1, you can rationalize the denominator, and you need to because you can't obviously leave this in the denominator of a final answer. Multiplying root 3 over root 3, you get root 3 of the numerator. Multiplying these two, of course, the square root of 9 just gives us 3. And there's your final answer simplified. Number 4, square root of 75 over square root of 3. We can rewrite this as root 75/3. And because 75/3 is nicely reducible to 25, and because the square root of 25 is even nicer because that's, well, a perfect square, the answer of which is simply just 5. Let's move on. Number 5, 8 root 2 over 2 root 8. If we continue here, hopefully we can all agree and see that in the context of rationalizing the denominator, yes, you could multiply both numerator and denominator by root 8. However, you could probably start this process with more simplification as such. We can divide 8 by 2 to get 4. And then again, you can rewrite root 2 over root 8 as one singular root and fraction, which is nice, I think, because 2/8 is reducible as follows, 1 over 4. So now you've got 4 times the square root of 1/4. And that's a nice thing because the square root of 1 on its own, that's just nicely 1. And the square root of 4 on its own is simply, what? 2. So you have 4 times 1 all over 2, of course 4 over 2, which is just simply 2. Okay. Another possible approach and a perspective that you can take is rewriting the square root of 8 as 4 and 2. And then of course, because 4 is a perfect square, you can rewrite it as follows. You can rewrite it as 2 root 2. And then here, the numerator is still root 2 from the beginning. The denominator is now 2 root 2 here. This 2 is still there technically, which I didn't multiply yet. But these are obviously the same. Therefore, when they divide out, you're left with 8 over 2 times 2, or 8 over 4, which again is just 2. So the answer is 2 no matter what. Number 6. So this particular problem, I went ahead and I combined I combined both roots as follows. I did 2 times 6 and 5 times 5. And I wrote it as one big radical. Turns out, nicely enough, 5 times 5, of course, is 25. So when you take the square root, you get 5. 2 times 6, which again, as you hopefully remember, when you break it down as such, 2 times 3 as prime factors should be written. You actually have 2 times 2 times 3. In other words, 4 times 3, which is still 12. These two values here, as they pair up together, give us a perfect square. And of course, when we take the square root of 4, we get 2. So the final answer, numerator 2 root 3, simplified. And like I said, denominator simply 5. Okay, we're going to take a look at maybe one or two more. Let me actually jump to a problem or two with variables. In particular, I think number 12 would be great to dig into. So this is a square root of a fraction, 75 b cubed c to the 6th over a squared. You can and should split up each individual root as such. So 75 b cubed c to the 6th, the square root, of course, all over the square root of a squared. 75 is not the perfect square, but the prime factors of 5 times 5 together are perfect square, a perfect square. 25, of course. 3 is remaining. B to the 3rd is b times b times b. There's a perfect square if you circle those two. C to the 6th is a perfect square as such. You can write it as c cubed times c cubed. That is a perfect square, the square root of which is 5. That is a perfect square, the square root of which is b. That is a perfect square, the square root of which is c cubed. Under the root, you're left with 3, and you're left with b. Denominator, as you can see, when I square root a squared, you have a. Remember, the absolute value is crucial anytime you are doing an even root of a variable and getting an odd exponent. So it's a to the 1st if you think about it, and that, of course, demands absolute value. Similarly, in the numerator, as you can also see, there's b to the 1st, therefore absolute value, and c to the 3rd, therefore absolute value. I'll say it again. When you have an even root, so a square root, a 4th root, and so on, and the answers that are variables have odd exponents, you must include absolute value. Let's continue. So in number 13, what we see is root 4 over 3 minus root 5. So we're going to go ahead and incorporate as something called a conjugate. Now you have not yet seen this, but please take a look. A conjugate looks very much like what you see in the denominator, 3 minus root 5, but what? 3 plus. Why is it 3 plus root 5? Well, as it turns out, again, the rule of which we are trying to abide by not leaving a root in the denominator of a fraction, when you multiply 3 minus root 5 times 3 plus root 5, what you're doing is multiplying by a conjugate, of course, to get the number to basically turn into a rational number as opposed to an irrational with root 5. So as we're about to see, let's FOIL the denominator. So 3 times 3, of course, 9. 3 times root 5, which is 3 root 5, and then 3 times negative root 5, which is negative 3 root 5, and then negative root 5 times positive root 5, which is simply negative 5. This is what we're hoping for in every single instance when we FOIL conjugates. The outside and the inside are going to cancel. Therefore, nicely 9 minus 5, of course, is 4. So what we then have just in the numerator to deal with is this 2, because the square root of 4 is 2. Distributed through, yielding 6 plus 2 root 5. And in the next step, you can see that accordingly. But as it turns out, 6/4 as a next step, you can reduce. And 2/4 you can reduce. So 6/4 or 3/2. And then plus 2/4, which is a half root 5, or root 5 over 2. Same thing. Let's finish up with number 14. 14 is root 8 over 2 plus root 3. Now to kickstart the problem, I actually took root 8 and I wrote it as the square root of 2 times 4 essentially, of which of course because 4 is a perfect square you get 2. So the numerator actually can be rewritten as 2 root 2. The denominator is still 2 plus root 3, but again, because as far as the rule goes, not having a radical or a root in the denominator, we rationalize by multiplying by the conjugate. Again, rationalize, multiplying by the conjugate. The beautiful thing about multiplying conjugates now is that because outside and inside, like number 13, are going to cancel, you really just need to do first 2 times 2, which is 4, and last, root 3 times negative root 3, which is negative 3. Distribute the 2 root 2 in the numerator, so 2 root 2 times 2, or 4 root 2, and 2 root 2 times negative root 3, which is 2 times root 6, technically minus 2 root 6. Almost done. 4 minus 3 is nice, of course. That's rational. That's just, of course, also as easy as not even writing it, or just, you can write 1 if you'd like, but you don't have to. So then the final answer simply is just what you see in the numerator, 4 root 2 minus 2 root 6. I do encourage that you take a look at some of those other problems maybe that we didn't discuss, and that includes problems with and without variables. We'll continue this another time.